So we practiced a little substitution last time, but we're going to do a few more here. So how do you know if you need U-substitution? I technically don't need it here. If I had enough time and energy, I could multiply this out to the 7th power, right? It would be really long. I could distribute the x to the 4th, and I'd have just a bunch of, terms, powers of x's, and I could integrate each one separately, right? But this is the advantage of U-substitution, especially if you've got something raised to the 7th. That's too much work, right? So let's run through it. I'm going to run through it the way I showed you guys on Thursday. And then I'm kind of curious, we'll find out, I want to hear how Stromer explained it. But anyhow, a good choice for you would be the stuff in the parentheses. We'll take this one kind of slow because I'm not sure everybody was here last time. So just by doing that, by letting this be u, we now have u to the 7th. But what is still unaccounted for is this x to the 4th and dx. And my goal now is I need to convert those two in terms of u's and du's so that I can integrate with respect to u. And that comes from the derivative. So it's really du dx. And I take the derivative, but then I just multiply the dx over. So it's 5x to the 4th times dx. And then, okay, the way I taught, let me just review this, and then I want to hear from feedback from Stromer's class here. The way I explain this, because I think it's just the most efficient way in the long run. It requires less writing. It's a lot faster. Okay, I shouldn't say a lot faster, but every second counts, right? When you're doing work on a test or something like that, it can be so much faster. Okay, so then it's the wishing technique, right? I have an x to the 4th and a dx, and I have one there. If there happened to be a 5 there, then I could just trade that all in and replace it with du. So my wishing technique is I need to see a 5 there, so I wish for a 5. I like to circle it because that wasn't there before. And then I compensate outside the integral with a 1/5. And so then the 1/5 will stay there. But then what happens, right, is that this 5, now with the x to the 4th, combined with that dx, is a straight trade-in for du. That equals du. And what I do from now, since the whole integral is in terms of u and du, I can now use, I can integrate this, right? Fundamental theorem of calculus part 2, I guess. Well, I don't have a definite integral, never mind. I can evaluate this, which is u to the 8th over 8. I guess it's technically like that because the 1/5 was factored out. And this will become, I'm going to replace my u and distribute. So I'll have x to the 5th plus 6 to the 8th over 40. And we can do this too. Remember, if c represents a constant, 1/5 of c is just, I could just still leave that as c. It's a different constant, right? Now, the part I'm curious about, that part that, depending on who's teaching, you use substitution can sometimes look a little different, is that wishing thing, okay? The way I do it is there's no real work I show other than wishing for that 5 and compensating with the 1/5. There are alternate methods. One popular method is without that 5, I have x to the 4th dx. So what you do is you solve for that by dividing by 5, and then you replace that with du over 5. The other method is to solve it for dx by dividing both sides by 5x to the 4th, And when you plug that in for dx, it cancels out the x to the fourth. So curious, how did Stromer, did that come up in class?
It did come up. I don't remember him dividing out anything.
Okay.
Okay, from what I'm looking at right now, when he did apply the wishing technique, he multiplied the du times whatever number you needed.
Yeah.
And then he essentially carried it out the same way you carried out the problem.
Oh, good.
There's not really a big difference. I'm
That's
sure
good.
whoever has Stromer could tell it's the
Okay.
same thing.
That's good, because historically when I teach this class, I mean, students want to know the most efficient way, but then the professor does it a little different, and then it can be confusing sometimes if they're doing a completely different technique. So that's one good sign. We'll see what happens when Barn gets there.
Yeah.
Again, it doesn't matter how you do it. Yeah, it doesn't matter if you use the wishing technique or whatever method your professor shows you, as long as we get to this result right here. Okay, one question asked here is, what happens to this? Does the du automatically become c? Not technically. I mean, you could almost think of it that way. What's going on with the du in this context is all the du is acting as is it's a direction. This right here says find the antiderivative of u to the seventh with respect to u, is how I would interpret the du in this context. So by finding the antiderivative and acknowledging there could be a constant there, because the derivative of the constant would have been 0, I've done what this told me to do. I've found the antiderivative with respect to u. So since I've done what it asked me to do, there's no reason to put du anymore, right? I did it. So that's really the explanation of why the du disappears. I'll just stay with that, I think. And then, yeah, again, if you have a constant, like if I had this 1/5 technically is 1/5 c, you could certainly leave it as 1/5 c or just replace it as c, right? 1/5 times a constant is just another constant, right? Maybe to denote it's a different constant, you could put like c1 or something, but no one's going to really do that. They'll just leave it as c. Okay. So for my next example, everything's going on in the denominator. If I had to pick one, though, I think I'd pick this because it's being squared. I would pick just the inside. And that's another thing to think about, like when you're choosing your u, I don't need to take the whole 7th power, like back on this first one. I don't need to let it be the whole thing, because if I just take the inside, that's u to the 7th. I can integrate that, right? There's no need to take the power. The other thing it'll do is if you take the power, it's going to mess up your du. Your du would be much worse. So in this case, I'm just going to take root x plus 3. So my du is 1/2 x to the negative 1/2 times dx, which is the same thing as, okay, well, I could do a couple of different things here. What I'm looking for, remember, if U-substitution is going to work, I should see at least this somewhere else in the integral. And do you see that I can, right? If I take this root x, and let me just rewrite this. So this is going to be u squared on the bottom. But if I take this root x and bring it up, it's going to be x to the negative 1/2, right? This root x is really that. And so all I need to wish for in this case to make it work out is put a 1/2 there, and this time compensate with a 2. So then this whole numerator is du. The bottom is u squared. And then remember to integrate it, unless it's just 1 over u to the first, what you're going to want to do is bring that up as u to the negative 2. And then power up, right? It's u to the negative 1 divided by negative 1. I get lazy sometimes. Sometimes I'll just do this, when in reality it really should be times the whole thing times 2. But again, that 2 times c I could just replace with c. So if I distribute this, this is really going to be negative 2 over u plus c, and then I'll put my u back in. Okay, so my next example, what should I let u equal, right? And there's all kinds of possibilities here, right? So remember that whatever you let u equal, du, or at least something close to that, should show up somewhere else. So I think we could rule out a lot of things then, right? If I let u equal cosine squared, the derivative of that is not going to have an e to the tangent in there, right? So there would be no way to get rid of that, right? I'd be stuck with that. So it's not going to be that. If I try letting u equal e to the tangent of 3x, this whole thing, the derivative of that would have another e in it, right? The derivative of e to stuff is e to stuff. But if I let this whole thing be u, I don't have any more e's, right, to become my du. So you kind of rule those things out. The only logical thing then that would be left is letting u equal the tangent of 3x. And also, I guess, to confirm that, if that's my u, I can integrate e to the u, right? We know how to do that, so that would be okay. Now, what's the derivative of tangent? This is a good time to remember your trig derivatives. It is secant squared of 3x times the derivative of the inside, which is 3. Now, okay, we first glance, it's like, wait, I don't even have that. But remember that 1 over cosine squared, this is really the same thing as secant squared of 3x. And then this is my u, and I still have a dx. I have not replaced that yet. But I can replace it. What's the only thing I need to wish for?
Three.
Yep. And where I put it doesn't really matter. I'm going to put it in front, compensate with a 1/3. And that together with this just becomes du. And my antiderivative of e to the u is e to the u. So this would be 1/3 e to the tan 3x plus a constant. So how about the next one? What would be a good choice for you? Yeah, I wouldn't want to let u be the whole sine, because the derivative of that would have a cosine, and I don't have that anywhere else, right? So the only thing I can think of is letting it be 1 over x cubed, which would be x to the negative 3. And my du here would be this time negative 3x to the negative 4, which we have, right? We can make that work, because this is, if I rewrite this x to the 4, if I bring it up, is x to the negative 4 dx. So this time I just need to wish for a negative 3, and I have a negative 1/3 on the outside. Oh, sine of u, and this is du. Yeah, these problems, at least the ones here that are u sub, they kind of make them, I mean, if this was x to the 5th here, we would have been in trouble. It wouldn't have worked, right? We couldn't, so they make them so that they will work out. Okay, antiderivative of sine. Careful, the derivative of positive sine is positive cosine, but the antiderivative is negative cosine. So this will turn into positive 1/3 cosine of my u.
Hey Grant,
Yeah.
I have a question. So,
Yes.
could you break down how you do your wishing technique again?
Yeah. So what I do is when I do my u and my du, I look, okay, this was my u, right? So I have sine of u. I look at what's left over, and is if my du is only off by a constant from what I have, right? What I have left before I put that negative 3 there, I was only off by that negative 3. As long as it's just a constant, then you can wish for that constant there and then compensate with the reciprocal outside, because that's just, you're not changing the problem. This times this just gives me 1.
Okay.
And then the whole reason for that is so that this part right here literally just equals du, so I replace it with du. But whatever you bring outside needs to stay there, right? That's going to come down.
Thank you.
Mm-hmm.
Grant,
Yeah.
when do we mostly use this substitution method?
A lot, quite frequently. Now, not all the time.
But for what specific situation do we, when do we use this?
Unfortunately, with antiderivatives, the rules are less clear. I can't tell you a situation where you'll always use it.
Mm-hmm.
I know it sounds, it's so unsatisfying to not know exactly when you'll have to use it. But I mean, usually you'll have two functions either multiplied or divided, right? Two different types of functions, because we know, right, according to our properties of integrals, if you got a quotient, you can't just find the antiderivative of that and then divide by the antiderivative of that.
Mm-hmm.
So with products and quotients, I would say that's a, yeah. This is why the more we do, the better you're going to get. So I know you have some homework on your WebWorks, but again, I don't know if that's enough to really feel. I would also be maybe doing some odd problems from the book so you can check your answers, stuff like that.
Do you have good problems for this in your web?
Yeah. If you go to my website, I have some here. I'm going to make sure everybody knows what. I got to share my screen here first. So on my, whoops, I had it here somewhere. Where'd it go? Oh, well, it's on 21C here. But if you just, I think I have my link to my website on the Canvas page, but if you go to 21B, if some of you who didn't have me last quarter, because I had the same thing for 21A, these problem sets, we didn't get to do this much even when we were in the classroom, but there was a time when, I don't know how we made it work, but maybe I just talked less. And we would get up on the board and work on practice problems. So like I've got problem set 4 is going to have some practice U-substitution integrals. There's some fundamental theorem of calculus. Here's some area problems, which we're going to talk about later. And the solutions to those should be up. Let me make sure. Yeah, so I've got solutions to all those. So it's not a bad thing to look at. And then, you know, as the midterms, those of you who have midterms, as they get closer, I've got some review problems and stuff there too. Ooh, sorry, I'm looking at my own stuff. So you might find, as we learn more integration techniques, right now we only are doing U-sub, but we're gonna learn some other techniques for finding antiderivatives like long division, partial fractions. There's this integration, this wasn't mine, somebody else came up with this like integration outline as sort of a guide to help you figure out what technique of integration you're going to use. Anyhow.
So there's a lot of techniques. So
there's a lot coming up, yeah. A lot of the other fancier ones will happen probably not till like week 7, 6 or 7, maybe 6. We learn U-substitution and then we practice a whole bunch of stuff with it, and then we start to get back into some of the other fancy techniques. So I'm trying to give you a good snapshot of different types of U-substitution problems that are kind of common, I guess. And so these next two have a theme too. And what that is here, okay, I have x times x minus 3 to the 5th. Again, if I wanted to FOIL that out and distribute the x, I wouldn't have to bother with U-sub, but who wants to raise that to the 5th? Not me. If I was going to choose a u, I would just choose what's in the inside of the parentheses. And I've been giving you a lot of messy U-substitution ones where you have to wish for something, but oftentimes you don't have to wish for anything. This is u to the 5th, and du literally just equals dx, so I can just trade that in for du. But what's the trouble is I have an unaccounted for x, right? And when we do U-substitution, we're committing to change everybody in terms of u's and du's. And so I've got a leftover x, and I can bring it down there, but I'm going to be stuck, right? If you get leftover x terms, sometimes you can do this. As long as there's a way to write that x in terms of u, I'm okay. So if I go back to my u statement, if u equals x minus 3, what would x equal? U plus 3, right? Just solve for x. And so I can take this and substitute it in for that leftover x. So maybe we'll say if you have leftovers, leftover x's, you can sometimes go back here and solve for x, right? Solve for x in terms of u. Now notice I'm not done. I still have a product, right? This was a product, this is a product, and we can't just integrate one and then integrate the other when you have a product. But what's much nicer about this, you can't just distribute this x into this to the fifth because you'd have to FOIL that out. But this is just u to the fifth, which I can easily distribute. And then I'll use my power rule. U to the 7th over 7, 3u to the 6 over 6, plus a constant. So that's going to give me, if I plug back in, I guess I'll reduce that to 1/2. I'll do x minus 3 to the 6 over 2. You know what I'm going to do for the next one? Yeah, the derivative of, oh, where was I? Yeah, right here. The derivative of, so I probably should have written this. The derivative of x to the first is 1, right? So it's 1 dx. And maybe I'll even go back farther than this. When I go from here to here, what I'm really doing is I'm doing du dx equals 1, but we're always going to multiply that dx over. So du is just going to equal 1 dx, which is just dx. That's how I got that term there. So I want to show you on number 6. I didn't think of this until now, just so you could maybe feel a little bit more comfortable that there's more than one way to do number 6. There's more than one way to do this integral. I was reminded when I saw that integration outline that I showed you from my website. I'll tell you what, let's do it kind of along the same lines as how we did this one, and then I'll show you an alternate technique to find it. Okay, so on this problem, I'm doing a U sub. I'm going to choose, even though it seems a little bit like it's not going to work, okay, because if I let u equal x squared, the derivative of that would be 2x dx. And we've talked about it's okay to be off by a constant, but all I needed to see was an x. I've got too many x's, right? I've got x cubed dx left over. But we can still make this work. The denominator is u. There is an x in x cubed, so I'm gonna fish it out. I'm gonna break up x cubed as x squared times x. And to satisfy the du, converting this to a du, I only need to wish for a 2, right? I've got x dx, so I'm going to wish for a 2, compensate with a 1/2. So this will now be turned into du, but what do I have left over, right? I have a leftover x, well, maybe I shouldn't circle that. I have a leftover x squared, well, I'm in a different color anyhow. But as long as I can change that x squared in terms of u, then I'm okay. So if I go back here, what does x squared equal? U minus 1, right? So this could be replaced. Let's take the next line here. That gets replaced with u minus 1. and the 2x dx becomes my du. Should make it split up. Split up, no, split up into that and this. Okay, I'm not done yet, but I've at least successfully converted this to u's and du's. And you should love this type of an integral. Who knows why I said you should love when you get an integral that looks like that? Why should you love that?
You break it out?
Yes. Right, you can put that heart around it, right? Shows you how much you love that. And this will turn into u over u is just 1 minus 1 over u. Split up. Okay, now we're ready to integrate. The antiderivative of 1, now be careful here. The antiderivative of 1 with respect to u is u, right? With respect to x, it's x, but we're doing with respect to u. So the antiderivative of 1 is u minus, and then this is our favorite ln, right? ln. And then once I found my antiderivative, I can substitute back in. So this was x squared plus 1 minus ln. Might as well just do that, plus c. I'm just going to leave it out like that. Why do I not need the absolute value?
That's always going to be positive.
Good. Does it hurt to have the absolute value? Not at all. So if you leave it on there, that's fine. I just instinctually took it off.
Hey, Grant.
Yeah.
Why is it always going to be positive?
Just x squared plus 1. It just so happens, right, that my u choice, anything you square and add 1, this will always be positive.
Yeah. That makes sense. Thank you.
Yeah. See, and if I was your teacher and you recognized that and took off the absolute value, that's the kind of stuff I'd give a bonus point for, but I'm not your teacher. Because then it shows me that you're paying attention, right? You're not just going through the motions. It's that you're really thinking about it.
Word.
Hey, let me show you another way to do this one, because this might actually come up on a different problem. You might need this technique. I don't think I've shown this to you. Another way. So one thing, and we will revisit this later on in the quarter, because we're going to spend a bunch of time integrating fractions. There's a technique called partial fractions that is a big one coming up later on. So I'll probably readdress this. But if you have a fraction where the degree of the top is greater than or even equal to the degree of the bottom, you can rewrite this with long division. Now that I said that, you're probably like, that's okay, Grant. But it's really not that bad. Let me show you. So like you could take, right, long division the same way, like if you have, 100 divided by 3, right, where the degree of the top is bigger than the bottom, right? When you divide it, right, you divide 3 into 100, and you get 33 with a remainder of 1, right? And so how do we write that? We write that as 33 1/3, huh? Or you could even write it as 33 plus 1/3. I wanted to show you with numbers because it looks a little different when you do it algebraically. So then if okay, so it's right off the bat, it's different, right? Because usually you'd say, how many times is this going to this? Well, think about this. What would you put here so that when you multiply it, what I want to generate is an x cubed, because I know this is going to subtract out, right? When I subtract. So I'd want to have an x there. That'll give me x cubed plus x. And if I subtract, that cancels. I have nothing minus x, so I end up with a remainder of negative x. So I could say it's x remainder negative x. That looks kind of funny, huh? How else could I write that? I could write that as x, I'm going to use this strategy, plus negative x over x squared plus 1. So then, the idea is just like 100 thirds could be rewritten as 33 plus 1/3, this integral could be rewritten as the integral of x. Let me just put the minus down, minus x over x squared plus 1. Right, that's just using this. And here's a good thing to talk about. I'm kind of glad I did this now. Whenever you have an integral with two things here, we'd have no problem integrating x, right? We can do that. How would you integrate x over x squared plus 1? Hopefully you see that as a U-substitution, right? If I let u equal the bottom, du would equal 2x, and I could make that work, right? But the U-substitution only needs to happen on that, not on this, right? So this is a good time. I know some of you have been talking about properties of integrals. I would split these up. So for that integral, du is going to equal 2x dx. So I just need to wish for a 2, compensate with a 1/2. This one's all ready to go. The antiderivative of that is x squared over 2. And this is going to turn into, the numerator is du, the bottom is u. And du over u, if it helps, you can always put a 1 there, right? 1 over u du has an antiderivative of ln of u. Now, just to show you, this was the answer we had when we did it with the U sub. Do you see that it can be justified to be the same? If we distribute this 1/2 on the answer we did up here to everybody, I would actually get 1/2 x squared plus 1/2 minus 1/2 ln x squared plus 1 plus c. So notice it does look the same, but I do have an extra 1/2 in this answer, right? Who remembers that discussion we had? I don't remember when. It might have been the first day we were doing antiderivatives. Is this okay? Are these the same answers?
Yes.
Yes, they are. Yep, the 1/2 could be incorporated into the constant. That's right. You could just call 1/2 plus c and call it c, right? And then it would look exactly the same. So I think it's nice to know that you could do some integrals depending on how you view it, right? There's a couple different techniques. I personally think the U-substitution was easier than doing long division, but we'll see there is a time we are going to have to do long division. So what's up? Oh yeah. This next one's probably not going to be an issue because we had a chance to review that, but I think the reason I was thinking of this, by the way, what should you do here?
Split it.
Split it, yeah. This is definitely a splitting one, right? Not U-substitution, just a splitting. But I think the reason I wanted to add this one is that I do get some questions a lot of times. You know, people will say, well, wait a second. How about this? Just to really make it, this is easy for you to do. Put a 3 there. Because a lot of people, you know, and I get it. I mean, one of the messages I'm trying to tell you is that if you're, what's a signal to use U-substitution is that if you tried letting U equal 1 part, the derivative shows up somewhere else. And by that criteria, you might be, hey, look, I got a 3x squared, right? And I got a dx there, huh? But what's the problem? I've got this plus 1, right? And remember the wishing thing? To be clear on the wishing thing, you can only wish for a multiple. You can only put a constant times. You can't wish for a plus 1 and then put a plus 1 over here, okay? So we can't add constants. Can't add constants to try to make du work, I guess, so to speak. Okay, but then yeah, we saw this earlier, right? Anytime, and I want you to be really trained on this, anytime you see one term in the bottom, that's almost always what we're going to do. If there's 2 terms, 2 or more terms, we're going to split that up. X squared over x cubed, this is going to leave me with 3 over x. And then 1 over x cubed, I'm going to rewrite that as x to the negative 3. I left this one down because that antiderivative is going to be 3 ln of x, whereas here I'm going to use my power rule. I'm not going to bother rewriting this one. That's good enough. All right, and then one more practice with U sub here, but I haven't given you any where it's a definite integral. And so I want to show you how you deal with that when you are using U substitution with a definite integral. Okay, now this one works out nice, huh? Nicer than the last one. Because if I let u equal the stuff under the square root, my du is exactly 3x squared. So I don't need to wish for anything, right? It's sitting right there. Those are the nice ones. Okay, so in terms of converting this, okay, this is the square root of u on the bottom. So I have u to the 1/2, and I have du on the top. So I have it sitting like this, okay? Now here's one place you got to use a little bit of caution. This was a definite integral from 0 to 2. But if I put 0 and 2 on there, technically that's not correct. That's not right. Does anybody know why?
Because you're going from the limits of u and not x.
Yes, yeah. We get used to not writing it, right? But if this integral was in terms of x, these are x values. And so what's wrong with this is I'm committing to changing my integral in terms of u, but I've still got my limits in terms of x, right? So that's technically not good. That's not correct, okay? So there are two options that you can do here when you have a definite integral. So let me separate here. I want to show you the two options here, right? So one option is this. Let's just leave them off. Let's just leave them off until we get back in terms of x. Okay, so how would I integrate that? I would bring this up. And then I would use my power rule where I add 1. So negative 1/2 plus 1 is positive 1/2. Divided by 1/2 is the same thing as times 2. I'm not going to put a plus c because I'm going to bring those limits back. And then what do we usually do after we find our antiderivative is we plug our u back in, right? So this is really x cubed plus 1 to the 1/2, which is the same thing as the square root of x cubed plus 1. And now that I'm back in the language of x, so to speak, I can go ahead and bring back my 2 and 0, right? Because these were x limits. And use the fundamental theorem of calculus where I just plug in. So I get 2 times the square root of 9 minus 2 if I plug in 0 square root of 1. So I get 6 minus 2. My final answer should be 4. So I guess if I had to describe this technique, what we're doing is leave limits off until later, right? Till you get to here, huh? I'm going to put 2 methods. You can either do this, or the other technique is, I said we couldn't put the 2 and the 0 there because those were x limits and our integral was in terms of u. If we could somehow convert our limits in terms of u, then we would be okay. And it's not that hard. If you go to your U-substitution, right? My U-substitution was U equals x cubed plus 1. So what would you get if x was 2, right? That was our upper limit. What would that be in terms of U? 2 cubed plus 1 would be 9, right? And if x was 0, this would be U, right? U would be 9. If x was 0, then U would equal 1. Now, the advantage of converting the limits here is that when I get to this step here, I'm actually going to pick it up here. When I rewrite this as u to the negative 1/2 du, I can now put my limits on from 1 to 9, because those are in terms of u. And when I get my antiderivative, which was 2 u to the 1/2, because my limits are already in terms of u, there's no reason to convert back to x, right? I could just plug in from 9 to 1, and you see I get the same answer, right? Whoops, 6 minus 2, I get 4. Now, here's my personal opinion on this. You do save, if you compare the methods, you do save, like right here on this technique, I had to convert it to x first and then put my limits in, whereas here I got to go straight and plug in my numbers. So I do save one step by converting the limits, but it comes at a big cost, in my opinion. I don't know if this has happened in class yet, but it will. And especially, gosh, online now, wow. Especially if your lectures are pre-recorded, there's no chance to even ask a question, right? Sometimes in lecture, you can like throw up, because here's what happens. I was very nice here. I was very specific. I wrote x equals 0, x equals 2. Oftentimes, we don't even do that. We just put the numbers there, right? And you're supposed to know what that is. So can you imagine what happens in class when the integral, let me back up here. Again, let's pretend I didn't put that there. This integral gets put on the board by your professor. It's 0 to 2. Your professors won't tell you, they won't tell you this part. They're not going to tell you that they're converting the limits. Okay, so what happens in class oftentimes is they're working on this integral, they don't show you this, and all of a sudden the limits change from 1 to 9. And I love to go watch lectures when professors do this, because I look around the lecture hall and I see a bunch of students whispering to each other, what happened to the number? Why is it 1 and 9 now, right? Everybody's confused. Okay, can you see that, why that would be very easy to happen, right? All of a sudden the numbers change, right? Especially if they don't write this, if they don't tell you that they're converting it. And it's very, very common. So my personal opinion, because I've done this too, I have confused people over and over again by just changing these limits from what they originally were. And I'll get somebody who was maybe looking away for a second and didn't see how I got those numbers. It just causes more confusion than it's worth. So I personally don't usually change the limits. I take that one extra step and stick with my original limits. But I think you should know this, because I'm going to bet your professors are going to do this. And when it happens, if you see the limits change, now you know why. I forgot, are Stromer's lectures live, or are they're pre-recorded, aren't they?
Pre-recorded.
Pre-recorded. How about Barnes? Barnes is live?
He has it live, but then he also records them so we can watch them later.
Oh, okay, yeah. So, but he's doing it live, so I guess someone could ask a question if he was teaching it.
That's why we're behind.
Oh, yeah. Yeah, well, that's the other issue, right? That's the other issue. Yeah.
Yeah, because he takes like a really long time because people are always asking a lot of questions, which isn't like a bad thing, but it just puts us behind.
No, yeah, I know. I get that. Yeah. It's really hard, right? In a class of 30, you have time to ask questions, but when you have 100, 200 students, you got too many questions. It's, yeah. Okay. Let's put away U-substitution for a little bit here and go back to talking about setting up an integral for the area between graphs.
Grant,
Yeah.
before we like move on from like integrals, can you quickly explain what happens when you're taking like what's it called, reverse power rule with -1 as the exponent?
Yeah, it doesn't work. If you try, so you're saying like if I have 1 over x and I rewrite that as x to the -1,
Right.
yeah, see, that's the one exception because that would turn into x to the 0 over 0, which is not defined. So anytime you see 1 over x, you just have to know that that's going to be ln of x. And you know, what if we do it in terms of u, right? If we have that, that's going to be ln of u. So that's the one time you don't bring it up.
Got you. All right, thank you.
And on the flip side, because then I know in the past I've had students doing this, like they'll see that and I'll write ln of u, and so then they'll say ln of u squared, right? No, that's right. So if it's anything other than 1, then bring it up as u to the -2 and do your power rule.
Got you. Thank you.
Yeah. Okay, hopefully you've had time to copy this area down. And so I want to show you both ways to do this integral, to remind yourselves that you have options. The standard way, many of your integrals that you get, I'm just picking ones that are interesting so that you're prepared, is to just imagine filling it up with vertical rectangles, right? If that's what we're doing. Remember, the integral is adding up the Riemann sum, which could be adding up a bunch of rectangles under your graph here. And I like to draw a few throughout the region. We were talking about last time, the integral will add up the areas if you tell it the correct formula for the area, which if you have vertical rectangles is going to be whatever your rectangles hit on the top minus the bottom times the thickness. So here's the different interpretation, right? The thickness of each one of those rectangles is a very small, infinitely thin increment of x, which is another interpretation of the d something, right? So this will be dx in this case. And our issue here is these rectangles hit y equals 8x on the top, but as I move past this intersection point, the following rectangles always bump into y equals 16 on the top. So I have a different top function. And so if that happens, what we're going to need to do is split this up into two integrals. This is going to be our dividing line right here. And I guess I should find out that point, huh? Okay, let's do that first. A lot of these you can do in your head. When does 8x equal 16? When x is 2, right? So that's 216. When does x squared equal 16? That would be at 4. So my first integral, my top function, well, I'm going to be adding up the rectangles from x equals 0 to x equals 2. And for that interval, all of my rectangles hit y equals 8x on the top, and on the bottom, they all hit y equals x squared. I mean, we do get, now that I'm teaching this, I don't know, something about maybe not doing it on the board or whatever. I'm seeing how we do get lazy with the algebra. It really is that. Really is times dx, but we just leave off the parentheses most of the time. So, okay, and then we're going to have to add the integral from 2 to 4 because we want to capture this area where my top function is going to be 16 and my bottom function is still x squared. Yeah. So I want to subtract 8x minus x squared because in this region, my top function, all of my rectangles. Okay, let's try with numbers. I think that kind of helps too. Let's say this rectangle right here, I don't have room. Let's say this rectangle happens right here at x equals 1. What I want to is a measure of the height of that rectangle. So how do I find how high it goes? I would plug in 1 for 8x, and so that's going to tell me 8. And how low does this go? I would plug in 1 to my bottom function, and that gives me 1. So the height of that rectangle is 8 minus 1, top minus bottom. And so for some random x value, the top is going to be 8x, the bottom is going to be x squared. That gives me the height. There, I'll write that down. This is the height. And again, the dx is kind of like your infinitely thin width. And so the top function transitions from 2 to 4 to being 16. Okay, maybe we'll do another one, but let's just do a setup for this one. To actually evaluate it, you would do your antiderivatives of both of those and plug in the 2 and the 0. You would use your fundamental theorem of calculus. Maybe what I'll do instead is let's talk about the other way you could have done this particular area. So this one was using vertical rectangles. Let's call this part A. But we did do one, I think, last time on Thursday where I showed you that I won't say this is always going to be better, but in this particular case, I might try using horizontal rectangles. Do I have another color? Let's see what I got in here. Yeah, this will work. Because the integral doesn't care. It's going to add up whatever you tell it to, right? It's just more, I guess, intuitive to put vertical rectangles most of the time. But if we imagine filling this up with horizontal rectangles, we could fill up this same region. And I guess one telltale sign where you might want to consider horizontal rectangles is noticing that they match up perfectly. This is a horizontal line right here, right? That top rectangle would line up perfectly. And if we do horizontal rectangles, then we're going to switch to find the length of one of those rectangles, we're going to do right minus left. And the other big change is that the thickness of those rectangles, we have to incorporate the width, now is a little tiny increment of y. So we're going to call that dy. Now there's an implication. This is the dual interpretation of the differential part. Not only does dy literally represent the width of the rectangle, but in terms of computing this rectangle, where I have to find the antiderivative, it's going to tell me I need to find my antiderivative in terms of y. So that means when I identify the right and left function, it should be in terms of y. Every rectangle we draw horizontally on the right hits y equals x squared, also known as x equals root y. And on the left, my rectangles hit y equals 8x, also known as x equals 1/8 y.
Can you use either or is one like specific?
Vertical or horizontal?
Mm-hmm.
Yeah, either or. On a, I think the goal, on the homework would be to choose the one that's going to be more efficient, right? I think it's easier to do one integral rather than two. If I was writing a test for 21B, I would have my students do it both ways. If it could be, I would make a problem up like this where I would want them to know how to set it up both ways because it's a skill we're going to need. Okay, I got a question here. Yeah, I got a question here that, there is a way, geometrically, I suppose you could make a different shape here and take like the area of something and subtract out. Like if I brought down a vertical line here, I could find the area of a whole trapezoid and then subtract out this area here. You can do stuff like that for sure. If you can justify it, I think this would probably be easier. Oh yeah, with limits for y. So these should be in terms of y, right? My limits here. And so the way to think of this is, where is my lowest rectangle? At what y value? 0, right? And my highest rectangle, the one up here, happens at a y value of 16. So I have different limits. But this integral should come out to be the same as the value of both of those integrals added together. And why don't we evaluate this one just so we can remember the fundamental theorem part 2. How much time do I have? It's 3:27. Okay. So your antiderivative of root y, that's y to the 1/2, will be y to the 3/2 over 3/2 or times 2/3. And then for 1/8 y to the first, the 1/8 stays there and it's y squared over 2. So this will be 2/3 times 16 to the 3/2 minus, I guess I'll make this 1/16 times, oh, that's nice, 16 squared. So I put the 16 into both minus what I get when I plug in the 0 to both, but that's going to give me 0 for both of them. (16 to the 3/2 is the square root of 3/2. I'm sorry, the square root of 16, which is 4 cubed, is 64. And 1/16 of 16 squared is 16. I'm just going to leave it like that. Now there is, you saw my reasoning for going with horizontal rectangles as the more efficient way, because I was always bounded by the same, right? The best option here was because my right and left function were the same throughout the interval, throughout the area. That would have been more efficient because vertically my top function changes. So that's why horizontal, I think, would be the best choice here. But another, I guess, telltale sign maybe to go with horizontal cross sections. There's plenty of these in the book. I'm sure you'll get some on your homework when you get it, where they write their equations already in terms of y. There's a whole bunch of them. And you'll see why you'll see why it's better to use horizontal than this one. X equals y squared. We know y equals x squared is a parabola opening up. This would be a parabola opening to the right. And then x equals y plus 2, that's easy enough to solve for y. That would be the same thing as y equals x minus 2, which would be a line with a y-intercept of -2 and a slope of 1. So I'm going to guess it's going to look something like this. So there's definitely some area. Now let's just do this one way. Let's decide what's the best way, whether to have vertical rectangles or horizontal. Which one do you think would be better here? Well, I kind of gave the hint when I said it at the beginning. But do you see why vertical would not be a good choice here? For much of the region, right, I have the same top and bottom. I could put some vertical rectangles. But once you get into this region, right, I mean, the top function is the parabola and the bottom function is the parabola, right? So that's already an issue. I suppose what we really are talking about is this would be y equals positive root x. This would be y equals negative root x. So we could deal with it. But you see, because my bottom function would change, whereas if I do horizontal rectangles, I'm always going to be between the same two functions on the right and left. So that is definitely the way to go here.
What do you mean it changes?
I missed that.
What do you mean it changes the bottom function?
Oh, like if I was doing vertical rectangles, right? A rectangle right here would have the top function be the upper part of the parabola. The bottom would be the bottom part of the parabola. But see, it changes here, huh?
Yeah.
Yeah. We are going to have to find these intersection points here, which is just the intersection. Since they're both solved for x, maybe we'll just set them, and we need the y value anyhow, right? So let's just set y squared equal to y plus 2. I can already see the answer. Does everybody see it? So that gives me y equals 2 and -1. Okay, that makes sense. So this one right here has a certain x value, but the y value must be 2, and the -1 must be this other point. It's something -1. But I don't really care. If I'm going to, I don't care what the x value is, because if I'm going to do this with horizontal rectangles, I'm going to be writing my integral in terms of y anyhow. My lowest rectangle is going to be at y equals -1. My highest one's going to be at 2. It's going to be a dy integral, right? Because that's the thickness. What does every rectangle hit on the right? They hit this line, but I have to go back to the form when it was solved for y, right? They hit y plus 2 on the right. And what do they hit on the left? They hit y squared. I'm not going to evaluate this one. Let's just leave it like that. Can you guys hear my wife teaching in the other room?
Nice.
Oh, okay. This microphone's good. I think it. She works with older people, so she's doing an exercise class online with them.
Dope.
I'm sure that your house now is filled with classrooms then.
Yes. Yeah, and then my girls now have started school, so they have to check in with their teacher online too. So we're all busy. Hey, if you'll let me do one, I just want to do one more problem to sort of plant the seed of what the idea of an integral and how powerful it is, and get into the next topic, which you will probably be discussing tomorrow in class, certainly by Friday. Is that all right? And then it shouldn't take the rest of the time, so we'll have some time for questions.
No.
No? Okay, I forget it.
I kid.
I guess, why am I asking, huh? You know I'm gonna. It's because I know you guys are nice. And this is where we're headed after area, is finding the volume of a solid. So the solid we're going to talk about here, if you think about the area in the first quadrant, bounded by y equals x cubed and x equals 2, y equals 0. So I've got this little sliver of area there. And this is an area. This isn't a solid, right? This doesn't have any volume yet. But the way we're going to generate a solid, you kind of have to use a little imagination here. Imagine if you took this was a flat piece of paper or something, and you revolve it around the x-axis. So you take it around this giant circle.
Hey, Grant.
Yeah.
Is this the washer or screw method?
It is. So, but imagine you swept it around the x-axis and it left its image everywhere you went. So you got a complete solid here. Okay, this is a complete solid now. This is, I guess, the bottom of it. Well, maybe I'll have this go through. Here we go. And if that's hard to imagine, I always start with this shape, because Oh man, hang on. Wait, no, never mind. We don't have any more. Oh wait, maybe we do. Hang on 1 second. Well, you're right.
Yup.
Okay, darn. What I was looking for was the my girl. What piece of candy does that remind you of on its side? Not nice try, Jordan.
A
I'm
Hershey's?
back. Yes, it's a Hershey's Kiss. It's a Hershey's Kiss. I went to go ask my daughters because I thought they got some for Easter, but apparently they have been devoured. I was going to put it up here to show you. So yeah, imagine this looks just like a Hershey's Kiss here, okay? And we're going to find, so it's a three-dimensional solid. The reason I wanted to at least show you this today is to get this idea across. To find the volume of this, when we do area, we're imagining chopping this area into thin rectangular cross sections, right? And we're adding up the areas of those rectangles. Well, here, remember that an integral is an adding machine. It will add together whatever formula you tell it to. We've been using it to add together the areas of a bunch of rectangles. But if I take some thin cross sections of this, right? If I cut through this very thinly, what is a thin cross section of that going to look like all the way through? Do you see that that's really going to look like a thin circular disc, right? Cross sections are thin circular discs, okay? And every cross section, right? The only thing that changes is the discs get, a little bit bigger radius, right, as we move along. Okay, but as long as every shape is the same, the integral can add up the volume for us. Now, we do need to refresh our memory on what is the volume of a disc like this. Think of this is no different than a cylinder squashed down and turned on its side, right? It's squashed down. And so usually we talk about cylinders, they have a height h, a radius r, let me use capital R. And you may remember the volume of a cylinder is pi r squared times the height. And so that is going to be our general formula. If you have a shape where your cross sections look like discs, pi is a constant, so we can pull that out. But we're going to go with pi r squared. Now think about your h. The height of that cylinder is legit, but this height right here is an infinitely, right, that's our height. But back to your picture, that's a little tiny increment of x. And just like with rectangles, we're going to call that dx. So our height's going to turn into dx in this case. Okay. Now what we need, so this is kind of our general formula, and this is called the disk method. By the way, this dx could be, in a different case, it could be dy, right? It's either dx or dy. Now, what I need to finish this off is I just need a formula for the radius. The radius of any one of these disks, this distance right here is my radius. But back on my picture, that's just the distance from the x-axis to y equals x cubed. So my radius in this case is going to be x cubed squared. And then just like with rectangles, with area, you need to tell the integral, where would you like to add up the formula, the volumes of these disks from? Well, you'd want to start at 0 and your last one would be at 2. And this would be a very easy calculation, right? To actually work that out, that would be x to the 6th from 0 to 2. Do my power rule. Oh, you know what I'm thinking now? Let me finish this. If you plug in the 2, you end up getting 128. 2 to the 7th is 128 over 7. And then you plug in the 0, you get nothing. You know what I'm thinking now? Some of you will know what I'm talking about. If you didn't have me last quarter in Code 21A, then how many people remember my dating problem from last quarter? The movie screen, remember that one?
Yep.
When we found the optimal seat for you to sit to take your date to the movie, right? To the movies. Well, you know what I'm thinking here, right? You could, you know, what Hershey's Kiss is a great gift, right? For if you're taking a date, huh? It's, you know, hey, and you could, as a further thing, you could present your Hershey's Kiss along with a derivation for the volume of the Hershey's Kiss to impress your date.
Probably should have done this before coronavirus.
Fred, next Valentine, I'm gonna ask you for some advice. You know, on what
That's
to do.
really good.
Yeah, we're gonna have to wait this one out, but you got lots of planning time here. Oh, that's funny. I'm gonna stop the recording.